Hi, this video is Unit 2 recapping of two things that didn't go so hot for everyone. First is this chart that you can see on the screen, and the second is about Lewis dot structures and their hybridization, bond length, and Vesper chart. Those are the three things.
Okay, so looking at the chart, here is the objective that we're covering. And what the chart basically is looking at is the amount of energy, and that can be the amount of energy as calculated by Coulomb's law as a function of the distance of the two atoms. So you can see as the atoms are far away, they are not very much attracted to each other. And I know that from the chart because down here, this negative part, anything lower than 0 is negative. That means it's an attraction. That means the two nuclei are feeling attraction between the two. Anything positive that's up here is repulsion. And that's according to Coulomb's law. When Coulomb's law is calculated and it comes out as a negative value, that means you've got your Q times your Q on top for Coulomb's law, QQ over D. You've got a negative and a positive, and they're attracted to each other. On the positive side up here, that means you've got either two electrons that are repelling each other too much, or two protons, two nuclei, which are positive, are repelling each other too much, and that's what's creating this positive part. So taking the chart as we move from the right to the left. The two nuclei are pretty far away from each other. They start to come in closer to each other. As they come closer to each other, I have an electron is attracted to its own nucleus, as well as the nucleus of the new guy coming around to him. At the same time that's happening, this electron of this guy is being attracted to the nucleus of the other atom that's coming towards him. And we reach this sweet spot down here at the bottom where the perfect kind of ratio is happening here, where you have it as close as you possibly can for both the electrons to kind of feel the nuclei of each side, but they don't have enough repulsion of the nuclei to push it away. If you start getting too close, then the two nuclei are getting too close, and you get a huge amount of repulsion between the two nuclei. So that's why our energy goes high into the positive zone. What AP wants you to know is what this bottom stuff is down there. Basically, the idea of how a bond is made is when you share electrons. And then the idea that it's controlled by the size of the atom's core as well as if there's a double, single, or triple bond. So let me take those both parts. Here is two molecules. They're both held together by single bonds. So the only difference between Br, and hydrogen is the size of the atom. Hydrogen, we know, is a very small atom, and bromine, relatively speaking, is quite large. So on the picture here, let's say the red line happens to be my bromines, is the red line. I'm going to put on there a blue line to represent my hydrogens. It should have a smaller nuclei there, so it should be over here on the distance, because it should be a smaller distance. I don't know that I'm not going to say the energy is any different because it's a single bond, so I'm not going to say that one bond is stronger than the other. So I'm going to draw my line like this. Okay, now if we move to the second idea, that's the idea of a double versus single versus triple bond. So I'm going to draw these in a couple different colors here. Now my N2 has a triple bond, my O2 is a double bond, and my H is a single bond. So if I were to draw those based on that, if I had N, I might draw it. A triple bond is very strong, so that means it should have a really big dip and then go all the way up. My O2, N and O are very close to each other on the periodic table, so they're relatively about the same size. Between the two, oxygen is a little bit smaller, but I don't know if I can really successfully show them the chart, so I'm not going to do it because I don't know it's big enough to even see that difference. So I'm going to keep mine pretty close here. I'm going to make my energy a little bit less here because that is not as strong when it's a double bond as if it's a triple bond. Triple bond is lower because it's a stronger bond. Then finally, when I'm looking at hydrogen, I'm going to have my bond strength farther up, but it is a smaller, like significantly smaller atom than the other, so I'm going to move it in further over here. So if I had to sketch what it might look like, it's kind of a little bit. I hope you can kind of see the difference of what I'm going for. That might be what the sketch looks like. So those are the things you're expected to know for that. The next thing is I wanted to talk about hybridization, Vesper charts, and we have to talk about Vesper charts, hybridization, pi bonds, and sigma bonds. Okay. As well as I want to talk about formal charge. Okay, so let's skip over to the VSEPR chart. On the test, it's open notes, so I would just straight up take the VSEPR chart. I think this is a good one. It's one I gave you in class. If you don't like it, maybe you want to look up a new one or something. But here we no longer have to memorize angles or names. It's just all right there. We have to be able to use it, though. You might even want to put in your hybridization as a lane if that helps you. That's kind of up to you. So let's take my picture that I have here and kind of look at its VSEPR shape. Each center has its own VSEPR shape. So you can't say this whole thing has a set VSEPR shape. I would have to say the center on this carbon, we're looking at linear. This carbon is linear, the two centers. Linear because it has two domains on either side, and there are no lone pairs anywhere. So there's two things and no lone pairs. It's not about number of bonds in each VSEPR chart, it's about number of things on either side. So although carbon has 4 bonds around it, 3 on one side, 1 on the other, I don't ever want to look at that. I just want to look at the things around it. So carbon has bromine on one side and then bonds on the other. That's two things, two bonded things. That's how I know it's linear. So if you look at this one here, I look at carbon. This carbon has 1, 2, 3, 4 things around it. The only thing that has 4 things with no lone pairs is the tetrahedral shape. That's right here. This carbon here has 1, 2, 3 things around it. Yes, I know there's a double bond there, but don't count each bond. You count each thing. There are 3 things around the carbon, none of which are lone pairs. That's why it's trigonoplanar. The oxygen here has 1, 2, 3, 4. In other words, it's north, west, east, north, and south are all covered. He has 4 things around him, 2 of which are lone pairs. So that's why I would call it tetrahedral. 2 bonding things, 2 lone pairs, not tetrahedral. So bent. Recap. It has 2 bonding things, 2 lone pairs. That means it's going to be the bent shape. Down here, this carbon has a tetrahedral shape because it has 4 things around it. This nitrogen has 1, 2, 3, 4 things around it. That lone pair counts as a thing. And so that would be called a trigonal pyramidal shape. 3 bonded and 1 lone pair. Now, when you look at angles, you can just basically read them off the chart. So you don't have to memorize things anymore. Like this is your 180 and such. When it gets to angles, like you have to estimate, like we did. Like let's look at this one. This is the only kind of like tricky one. Right here, I would say that's trigonoplanar. So if I drew it in the real shape, these would all be equidistant from each other, and I call it 120. And in fact, if you would say on the AP free response test 120, they would count that. They have counted it on all of their answer keys. Technically speaking, these double bonds are a little bit fatter. So a better answer would be these fatness, meaning so many electrons are living in there, it creates this big fat region that pushes things away. This angle here would be a little bit greater than 120. I would say like 122. And then this would be 122. And then this angle down here would have to be less than that. So 4 less than that, 116. Right? That's right. Something like that. But if you actually stuck with 120, you would be fine there. Okay, then I wanted to talk about hybridization. So hybridization is based on its VSEPR structure. Actually, it goes the other way. Because things hybridize, you have VSEPR shapes. But again, you want to count the number of things that are around it. Here I've got 1, 2, 2 things around this carbon. I would call it sp hybridized. Same for this carbon, sp hybridized. If I look at this oxygen right here, it has 4 things around it. 1, 2, 3, 4. Lone pairs count, so I call it sp3. So that would be 1 s and 3 p's, and that adds up to 4. This carbon in the middle here, that has 3 things around it, so I call it sp2. This carbon here has 4 things around it, sp3. Moving down to the bottom, same kind of carbon, sp3. And then this nitrogen here has 4 things around it. 3 bonding things and a lone pair, that makes it sp3. Something about the AP test is they will not have you do any Lewis dot structures. And I know that because they will not allow any drawing. Their program only allows you to type things and do like equations for things and not drawing. So you will not have to do Lewis dot structures. What that means is they will give you a Lewis dot structure and your job is to decide how good it is at the maximum. Which is why I'm drawing the Lewis dot structure here. This is a resonance structure situation. Your job would be to decide which structure, which drawing is the best one. So that's when we got to look at formal charges. Taking a look at formal charges, I would say that I count how many electrons are around something and then how many it wants. Like carbon here, carbon would want 4 electrons around it. That's how he's the happiest. Nitrogen wants 5 electrons around it. Oxygen wants 6. And I know that because that's how many valence electrons they are. In other words, nitrogen comes with 5, he wants 5 around him. Carbon comes with 4, he wants 4 around him. Oxygen comes with 6, he wants 6 around him. So now we're going to count like how many does he really have. Like nitrogen, he has 1, 2, 3, 4, 5, 6. He has 6 electrons around him. That's 1 more than he really wants. His formal charge is a 1 minus. Should say 1 minus, minus 1. 1, like that. Minus 1. This carbon here has 1, 2, 3, 4 electrons around it. So its formal charge is 0 because it got 4 and it wants 4. Good. This oxygen over here has 1, 2, 3, 4, 5, 6. 6 around it. It has a formal charge of 0. Now if I added up all these formal charges, 0 plus 0 plus negative 1, I get a negative 1, which is good because this is a polyatomic ion and it adds up to a minus 1. So that works out. A first quick check of things is to check, do all your formal charges add up to what it should? If it doesn't, you might have done something wrong, or it's just a structure that doesn't exist actually. Moving on to the next one. This nitrogen here is 1, 2, 3, 4, 5, 6, 7. 7 electrons. It really doesn't want 7 electrons. That's 2 more than it wants. That's a minus 2. This one here is still a 0. And this one over here is 1, 2, 3, 4, 5. That's 1 less than it wants. That's a plus 1. And looking at the bottom one, 0 on this carbon, 1, 2, 3, 4, 5. That's a 0. And this side has 1, 2, 3, 4, 5, 6, 7 electrons around it. That's a minus 1. Now I have to decide which one is the best structure. The best one would be the one that has the more electronegative element has a negative charge. The most electronegative element is oxygen in this group, so I want one with a negative charge. I can see this one is a positive, this one is a 0, which is okay. If they were all 0, that'd be pretty nice, but that's not possible here. So this bottom structure is the best one. The reason is because oxygen is most electronegative, and it has the most negative formal charge. Okay. Let me double check the test. Pi bonds and sigma bonds. Let's hit that really quick, and then I think we're good. Looking at these pictures, so the first bond is always the sigma bond. So right here in the triple bond, that's a sigma bond. That's the first bond. That would mean it has 2 pi bonds. This one's here is 1 sigma bond, 1 sigma bond. Down here, these are all sigma bonds because there's no double bonds. In this molecule here, I would say there's 1, 2, 3, 4, 5, 6 sigma bonds. And only, 1, 2, 3, 4, 5, 6, 7. 7 sigma bonds. One of these double bonds is a sigma bond, and the other one is a pi bond. I think you guys did good with that in the first time, so I don't have to keep that too much. All right, that's the end. Good luck.